Okay, so let's start with our topic today. We're going to continue with our radar related concepts. In the last lecture, we learned an important trade-off for a radar measurement. We said that in general we use radar measurements to measure range, which is the distance of the target, and also the velocity or the Doppler shift due to the moving target. So our goal is generally to measure these two quantities at the same time. And in the last lecture, we learned that for measuring each of these, we need different characteristics for our transmitted radar signal. So it is not possible to design the best waveform or choose the best radar signal to measure both of these quantities in a good way or in the optimal way at the same time. So we need to kind of decide on the trade-off between these two, how much we want range resolution, how much we want Doppler shift or velocity resolution. And that trade-off is mainly characterized by ambiguity function. And we're going to discuss the concept of ambiguity function because of this. But let me here mention one thing. Ambiguity function comes from the motivation that, or comes from the fact that the received radar signal will be processed with a quadrature demodulator. Okay, so here the definition of ambiguity function actually arises from the fact that we are using a quadrature demodulator with the radar system, okay, within the radar system. So it's a function specialized for this demodulator type. Okay, so we need to first understand how quadrature demodulator works and how does range and Doppler measurement are seen at the output of the quadrature demodulator. And then based on that, we're going to decide on how to define the ambiguity function to understand the trade. Okay, so that will be our main task in today's lectures. So let's first understand the quadrature demodulator, what it is. So in the quadrature demodulator, we will have a bandpass signal as the input. Okay, so the bandpass signal, we can think, for example, a bandpass signal of this form. Okay, so it has content around a high frequency F0, okay, both in the positive and negative quadrant. Okay, so it's a bandpass signal. And this is suppose our input. In a quadrature demodulator system, we have modulation, which is basically multiplication, with two sinusoidals. The first one is cosine 2 pi f0 t, and the second is sine 2 pi f0 t. So we're going to have as the second modulation function, we have the sinusoid 2 pi f0 t. And here the knowledge of f0 is available for us, okay, because f0 is basically the carrier frequency we use for our radar system, and that's our design. Okay, so we know that frequency. So we know the frequency of the bandpass signal, or the where the frequency content of the bandpass signal is centered. Okay, so we know these f0s, and based on that f0, we have two sinusoidal signals here that modulates the signal. And after each, we have a low pass filter. You can think it's an ideal low pass filter for simplicity right now. And let's call the resulting outputs S bar RT and S bar IT. Okay, and we're going to define, because this is two signals, we have two signals at the output of this quadrature demodulator. We want to define a single function that contains both of these two functions, and for that we use complex numbers, okay, or complex baseband representation. So we define a single S bar function which contains this SRT signal as its real part and SIT part is its imaginary part. Okay, so we define SRT as SRT plus J times SIT. And this actually denotes the real and imaginary parts. So now once we write SRT, now we can think the quadrature demodulator system as a single input, single output system. Okay, and we can apply all the things we learned in basic signals and systems theory course. Here, the special name we give to SRT is complex baseband representation, because this is going to be a signal that has low frequencies. It's going to be centered at 0. If you compute these mathematical operations, okay, you can find that the Fourier transform of SRT will only contain the portion of the input signal in the positive quadrant shifted to the origin by F0. Okay, so this quadrature demodulator operation mainly does that. So it takes the positive quadrant portion of the signal and shifts it to the origin. Okay, so you're going to get this thing. You can easily prove this relation by simply using this modulation and low pass filtering functions. Okay, I'm not gonna do the proof of that. Maybe I can give that to you in the homework, in your third homework, to prove this. So you can easily prove these relationships. Okay, so this one I already told you, S bar T is gonna basically be this operation, taking the positive portion of the signal and then shifting it to origin. Or you can express it in this form, in a mathematical way. You can say that you're gonna shift your input signal by F0 to the origin, so that in the frequency domain. In the time domain, that corresponds to multiplying S of t with a complex exponential with frequency minus F0. Okay, so that's going to shift your complete signal to the origin or to the left by F0. Then if you apply a low pass filter, you're going to get this shape, okay, or this portion of the signal. And similarly, you can also find the relation between the input and output. S of t you can obtain if someone give you the output of the demodulator system or the complex baseband representation of the signal. Just like we discussed before, you can obtain the passband signal by first modulating the signal with your high frequency or with your carrier frequency F0, and then taking the real part. Okay, so that will convert your complex baseband signal to its passband version. Okay, to S of t. So we have these relations between S of t and S bar t. Note that here we have cosine 2 pi f0 t and minus sine 2 pi f0 t is our modulation functions. When that's the case, this is our relationship. Let's look at few practical examples, actually commonly used radar signal types in both bandpass form and complex baseband form. For example, if you want a complex baseband signal of a Gaussian form, which is like in the form of e to the minus alpha t squared, okay, then that means if that's what you want to obtain, then you can simply insert this expression into this one, okay, to find what should be your receipt or what should be the input of the demodulator system or the transmitted radar signal, basically. Okay, so if you insert this one here, then take real part, you're going to get e to the minus alpha t squared times cosine 2 pi f0 t. So the real part of this term. So this is nothing but a Gaussian signal modulated with a sinusoid signal with frequency f0, okay, and that's going to look like this one. So that's the Gaussian pulse. So this is what we're gonna process after the demodulator, and this is what is physically received or transmitted by the radar system. Okay, so you should think that the quadrature demodulator is embedded in the radar system. Okay, so this you can think is your received signal. Okay, received radar signal. You are going to process it with the first with the quadrature demodulator and convert your bandpass signal to a low pass signal, and then do all your processing on this low pass signal. Okay, so all of your processing will be basically in this Gaussian pulse in this example. Okay, and this is going to be what will be received as a radar signal, and this is going to be what you will process. Okay. Let's look another example. Another commonly used radar signal example or radar pulse example is linear FM pulse. This is also called as a chirp pulse as well. In this one, the baseband representation is a chirp function. Okay, what was a chirp function? In the chirp function, we have a complex exponential, but its frequency varies with a square of the time variable. Okay, so we have e to the j pi t squared. Here there's also an alpha constant. And normally the chirp signal has infinite extent, but practically that's not possible. It will always have a finite extent. So to mathematically model the finite extent of the radar signal, we also multiply this with a rectangle signal of with t, okay, capital T. And this is called linear FM pulse. If we look at the baseband, complex baseband version of the signal, again, we need to take a real part of this signal, multiply with e to the j 2 pi f0 t. And if you compute that, the only complex part is now this portion. Okay, you can move the rectangle outside the real part. And the real part of this complex signal is going to be cosine 2 pi f0 plus alpha over 2t times t. Okay, so if you look at the frequency of s of t, that's what you have in front of t. So the frequency is going to be f0 plus alpha over 2t. Okay, or you can think it's the derivative of this with respect to t. And in this frequency, you see that the frequency of the signal increases with time. Okay, so it increases with time, and alpha determines actually how fast the frequency increases. Okay, if your alpha is greater, you're going to have a highly oscillating behavior in your linear FM. If your alpha is smaller, you're going to see slower variations. And so here you see the demonstration of that as well. If you want to plot the baseband signal, okay, because it's a complex value signal, you need to both plot its magnitude and phase. Here we have the magnitude. We take the magnitude of the signal. This term will not have effect. You're going to only see the rectangle signal, okay, with capital T. And if you look at the baseband signal, this is already a real value signal, so you can plot that. It's just actually a sinusoid whose frequency increases, and you modulate that with rectangle signal. Okay, and modulating or multiplying with the rectangle signal just defines a finite extent on the signal. Okay, so basically it defines this finite support. The effect of rectangle is this. And here, in this portion, you'll see the cosine signal with increasing frequency, okay, with time, okay, and you see that here. And that's going to be your baseband signal or low pass signal, okay, that will be processed. Now we want to understand actually if you are you're building a radar system, you will decide on which radar pulse to use. Okay, what should be my S of t or my S bar t to use to do best delay measurement or to get best velocity measurement. So to answer that question, you need to understand the effect of delay and frequency shift or velocity in your demodulator output. Okay, if your received signal carries this delay and frequency shift information, how will that carry to the output of the demodulator system? Okay, so suppose your received radar signal has arrived from a target with a certain velocity, and you want to learn the range and velocity of that target. You need to understand the effect of those things in the output of the demodulator first, okay? Because based on that, you're going to do processing after the demodulator. But as I said, demodulator is always there. It's the first processing we have in the radar system. Okay, so let's understand the effect of delay and frequency shift in our demodulator system. So we said that if S of t is our input to the demodulator system, our output is S bar t signal, okay? And it's simply mathematically related to S of t in this form. Okay? Suppose we receive a delayed version of the signal, okay, a received signal. So we have a radar pulse, but we receive it with a delayed tau. What will be the effect of this delayed tau at the output of the demodulator system? Okay, let's look at that. We want to compute basically this function, low pass filter of the received signal, okay, which is st minus tau, times e to the minus j2 pi f0 t. And if you look at this function, okay, so you can write this complex exponential term as e to the minus j2 pi f0 t minus tau, and also add this tau term here to get the same function. Okay. Now, if you look at this function, because low pass filtering is a linear operation, okay, so you can think that this is just a constant because it doesn't depend on the time variable t. You can move this constant outside this low pass filtering operation. Okay, so you can move it here, and this term. Now, if you take low pass filter of this term, this is going to be, you already called the low pass filter of this function S bar t. So you see that this is nothing but the time shifted version of S bar t with tau. Okay, because low pass filtering is not only linear operation but also time invariant operation. Okay, if you delay the input by tau, this is going to be the output. Output delayed by the same amount. Okay, so this is S bar t minus tau. So this is what we will observe at the output of the demodulator system for a delayed radar signal. So what do we see? Let's interpret it. Our demodulator output signal is also delayed compared to what we received before. Okay, so we have the same delay amount on the demodulator output signal, and there is also here a constant phase term. It doesn't depend on t, it's just a complex factor, so you can mostly ignore this term. Okay, so that's for delay. Let's also look at the effect of frequency shift in the demodulator input. So suppose this is the frequency content of your bandpass signal. Okay, so it is centered, its frequency content is centered around f0 and minus f0. So at the demodulator output, what we know that we're going to see this portion of the signal shifted to the origin. Now, if there is a frequency shift in your S of t signal due to the velocity of the target, okay, that was hit by the radar signal, that means your S of t is going to in the frequency domain, your S of t signal will be shifted by this frequency amount. Let's call that V. Okay, and the demodulator output will again be this portion shifted to the origin by f0, and that means you're going to see this portion of the signal by a shift of V. Okay, in the frequency domain. So you can simply think that your actually your output of the demodulator output will be the complex baseband signal shifted by frequency V. Okay, that's going to be going to what you will see. Okay, so you're just going to increase the frequency of the complex baseband signal by V, which is going to correspond to in the frequency domain by a shift to the right by frequency V. And that's going to be the amount of effect of frequency shift. So what do we see? On the time domain demodulator output, we see that our signal is modulated with a complex exponential signal. Okay, so this is not a phase anymore because it varies with t. So it's a complex exponential signal with frequency v. Okay, so we get that effect due to the velocity on the target. Okay, now that we know these two effects, now we can understand how to design this radar pulse, okay, to get good frequency and or velocity and delay information. So let's consider now this setting. Our demodulator signal, the input of the demodulator system is a returned signal, R of t, which is delayed and frequency shifted, which is a delayed and frequency shifted version of your original radar signal, S of t. And there is, of course, some noise on top of that. Okay, so we receive this return signal due to a moving target. If that's the case, how can we estimate the delay and frequency shift? Okay, after the demodulator. So here, maybe some of you know about the concept of match filtering. Okay, so here, the idea is to use the match filtering. So let's remember what was match filtering was for. If you have a signal S of t plus N of t, okay, and if you wanna detect here the signal S of t, okay, so if you wanna detect a signal that is buried or that is embedded in noise, okay, then you can process this signal with a filter H of t, whose impulse response is H of t, and that basically corresponds to your signal to be detected, okay, but it's conjugated and inverted version. So if you choose the filter response as S conjugate minus t, okay, then you're going to get for y of t the maximum signal to noise ratio, or maximum peak. We're going to observe maximum peak for y of t. That's actually this optimality is guaranteed. So you can prove that match filter is optimal in the sense of SNR. Okay, when your noise signal N of t is a white Gaussian noise signal. Okay, so under that assumption, this is the optimal operation to perform. And in most radar systems, we are basically using this match filtering idea. Okay, so let's try that. Let's consider our match filtering operation, which is following our demodulator subsystem. Okay, so our R of t carries the delay information or the range information and the velocity information of our target, and that's input to our radar system, and the first component is the demodulator, and we discussed that we're going to see at the demodulator output this portion, okay, due to the delay tau 0 on this one, and we're going to also get multiplication with this term, okay, due to the velocity information carried in R of t, or due to the frequency shift in R of t. So the overall signal we're going to receive or we're going to get at the output here is going to be this signal. And there will be also a term due to noise. So this is going to be a noise baseband representation term. And here we're gonna pick, we're gonna process this demodulator output. Okay? Let's say that we're gonna process it with a filter h of t, and let's call our output y of t, which is gonna contain both a signal part and a noise part. Okay. Here, the important thing is, of course, we don't know the delay, tau 0, because we don't know the range of the target. And we also don't know the velocity of the target, which is V0. So these are unknown to us, these values. So we're going to design our filter h of t to match to these values, okay? But we don't know them. We're going to pick different, let's say we pick tau 1 and V1 as our values. And we're going to design a match filter with the same. We're going to design a match filter for this input signal, okay, which is going to be basically conjugated and inverted version of the signal. But because tau 0 and V0 are unknown to us, we're going to assume they are tau 1 and V1. Okay? So our h of t will be this signal inverted. Okay, so instead of t, we're going to write minus t everywhere. Okay, and we're going to also take conjugate of the signal. So we're going to get plus here, and then another, this minus will be plus here. So this is going to be our signal match filtering response. And because tau 0 is not known, we're going to use just tau 1, and V0 is not known, we are going to just use V1. Okay, so this is, suppose, our match filters impulse response. Let's now understand our output signal y of t. As we said before, this is going to contain two terms, one term due to signal, one term due to noise. As the first thing, let's understand the signal part of the input. Okay, so let's understand YST. What is going to be YST? YST signal is actually gonna be due to the signal portion of the portion of the input signal to the system. So we're gonna have this portion of the input convolved with h of t. Okay, so we're gonna have this convolved with this. Here we're ignoring this complex factor here because it has no importance. Okay, it doesn't change with time. So if you ignore these terms, simply actually you don't even need to ignore, because okay, let's ignore them. And you're going to just get this thing convolved with this thing, okay, with ignoring this term. So this will be your signal portion. To find this thing, you need to compute the convolution. Okay, this is going to be a convolution of this with this one. Let's open this convolution relation. Because here there is reversal operation as well. I'm gonna use my temporary variable u to for this function. Okay, so here I'm gonna write instead of t, use everywhere, and then I'm gonna multiply this with this function evaluates at t minus u. Okay, so we replace t with t minus u here, and then integrate with respect to u. So that's our convolution signal. And remember that match filter tells us that we're gonna get observe a peak at origin. Okay, that's the principle of the match filtering. It's gonna give us the maximum peak at origin if we choose our impulse response in this form. Okay, let's look at what we're gonna see at the origin for this one. Okay, so I'm gonna look at the signal portion of my signal evaluated at 0, so at the origin. So instead of t, we're gonna just insert zeros here. Okay, if you do that, you're gonna get this form simply. Okay. So this is going to be the signal portion of the signal. And will you get this peak? Will you really observe the peak if tau 1 and tau 0 exactly match to each other or not? Okay. So I want to think about a little bit of this function. Okay, think about how the signal portion will look like and how we will define the ambiguity function based on this. Okay, so try to understand the effect of delay and effect of Doppler shift on this match filter output. Okay, and we're going to actually use. You can think you're going to use multiple of them as well. Think about those. Let's take a break now before continuing on this one, and we can continue with this in the next lecture.